Okay, so we will start. So we were having some trouble in understanding the example that was trying to motivate that a choice of n is important, and if you choose n as prime, that is typically seen to be better. Uh, so the example that I was giving you was the following. The keys contain the following numbers. Okay, and we said that one choice could be n equals 100 and the other choice could be n equals 101. Okay, so let us draw the two scenarios. Now let us consider the key values what will be the hash code, assuming that h of key is equal to key modulo n. So what will be the hash code of 205?
5.
5. 305? 5. 405? 5. 505? 5. So a single hash code here collides with 3 other hash codes. Let's take another example. Okay, so a single hash code would collide with 3 others. Now what happens if I choose n equals 101?
Sir,
Yes,
for 100 case, in the case if you take k as 200, 300, 400, 500, 600, then it will be 4 others.
that's the only pathological case where it will be 4. For all other cases, it's 3.
Okay.
Okay, so now when we take n equals 101, so let's say again key is 205, 305, 405, 505. What is HK?
3.
3, 2, 1, 0. Okay. Similarly, what is HK? So no collision. So in fact, if you take any number from this set, of this particular set of numbers, if you take any number, you will see none of them will collide.
But sir, if we have all the numbers from 200 to 600,
That's not the situation. The situation, you missed out the situation last day. So the keys are appearing in this. So do you understand why this set has been created in this way?
no sir.
Number of
No?
elements 100. Oh, one of them.
So basically, each number in this set actually utilizes a separate key position. Okay. If you get a key composition like this, then each number will use a separate position in this table of 101. Okay. Whereas if you choose n equals 100, then they are going to inevitably collide. So this is trying to motivate that for choice of like key values, for different choices of key values, it is arguably better to choose a prime number because it spreads the elements. Okay, it spreads the elements in the key set across the table. So it has a greater power or a greater potential to spread the elements across the table compared to something that is non-prime.
Sir,
Go ahead.
sir, I think here we can choose n, which is, I mean, a number which is co-prime with every element in the key set.
You can choose. You can choose that also. You can
Even,
choose that also. As long as it is co-prime with all the other elements, you can choose that also.
Sir, here we can choose
That
the
will
hash function
that
like
that
key
will
divided by 5.
reduce. Huh?
If we choose hash function key divided by 5, then also each element will
So
be.
what is 5? So what is the nature of 5?
So that is also prime.
What I am preaching is that I am actually preaching that the n that you choose should be typically prime. Okay, and there is a theoretical idea that is built on this, which we will not cover in this particular course. But when you go ahead and say study cryptography and cryptographic architectures in details, especially when you study about digital signatures, you will get to know about something called universal hash functions.
So about the choice of n, won't it depend on the set of keys?
Whatever the key set of keys are, like
So
on a on
if
a
the
on a random choice, like always, or on a in an arbitrary setting, always having a prime number n is important, or is suggested. Yeah, now go ahead.
so if the in the key set, if every number is means multiple of that prime, then all of them will give 0.
Every number is a multiple of that prime, of
Yes,
that single prime. So can you imagine how big that table would be? You are also
terribly
limited.
big.
Yeah, you are also limited by the memory size. Usually
Yes.
such bad keys will never be chosen. Okay,
Sir,
so
if the key set contains the multiples of prime, we can choose some composite number which is co-prime with all.
that's what we said. So coprime is also okay, but it is always suggested to have a prime number. That most practical purposes that solves your purpose, because it is always going to be coprime. I mean, uh, in like in a guaranteed number of cases, it's always going to be a coprime. So that is why, like, we typically vote for having um, uh, a prime number rather than a co-prime number, because your keys like are coming in on the fly, and you really do not, in many cases you really do not have a control. Like, we'll see an example just now, like the polynomial hash function. If you see, like, you really do not have a control on the keys that are generated. So therefore it is always advisable. So a priori keys are known, that is something very fortunate, okay, for a designer. So most of the times a designer will face with keys that are coming from some random stream, okay, and therefore, like, the most judicious choice would be to have a prime number which is like guaranteed to be co-prime with everything except for its multiples.
Sir, if we
Yes.
choose a prime which is co-prime with every other element of the data set, then how does it ensure that means on taking mod we will get unique remainders? Means in this case it happened, but how will we be sure? It might so happen that there are more number of collisions even if it is co-prime.
Why
Means
like,
remainder
if you are
does
choosing,
depend on
if you
divisibility, right?
huh
The remainder which we obtain on division, that does not depend on means whether they are co-prime or not. Means even if I choose a prime, how will it ensure that two different numbers which are co-prime with this prime number will not leave the same remainder?
so I don't get your point. So
So like we have a data set, right? And we are
uh,
choosing a prime number.
uh,
Then and the how does it ensure
no,
that
there will be, see, there will be always collisions. There will be, so as we said, collisions are unavoidable. It's only a design choice. Having prime numbers actually reduces collisions. That is what is the like point that we are trying to make. Having a composite number actually increases the number of collisions compared to a prime number. Okay, that is what is the main idea that we are trying to preach.
okay, sir.
It's not that collision will not happen. It's
Oh,
impossible to have. So last day we saw this birthday problem, right? Were you there in the class?
yes, sir. Yes.
Yeah. So collisions are unavoidable. That's not possible. It's only that we try to spread the keys better, and we hope that, like, since we are choosing a prime number, we will have much lesser collisions. That's the idea.
Okay, sir. Yes.
So,
Okay. Yes.
so since we don't know what type of keys we are getting, how to choose that prime?
So basically, you will have some idea on the on the uh, overall data size that you are going to like be faced with. Say for instance, like, say when we were discussing about this English words example, and suppose you make a ballpark, like, say, okay, I will allow 50,000 English words at a point in time. Okay, 50,000 words. So this automatically kind of gives you an idea of, like, what is going to be a suitable choice of n. Okay, and you try to choose a prime number close to that memory size. to the desired or in many cases available memory size. So this is always guided by the amount of memory that you have. The only idea is that close to that memory limits, choose a prime number rather than a composite number. Does that answer your question?
Yes, sir.
Sir, what if we choose that in the above example, what if we choose the keys to be 202, 303, 404, and 505? It will give more collisions with 101 and less with 100.
I don't understand. Which problem are you talking about?
So this example, which in which you choose 205, 305, 405, 505, that keys.
Yes.
Sir, what
So
if we choose
I
202?
just now told to one of your friends, right? You will never have such a bad choice of keys.
Yeah, okay,
That
okay, sir.
which is like a multiple of your initial prime.
Okay, sir.
Okay, so we were discussing this problem last day also. So, and we said that this is one of the nice ways of designing keys. Of course, it is not as good as the universal hash function, but it is a good way of it's a good choice for like designing keys. So let's say we have the string, okay, and we are trying to say hash elements in the English dictionary. So our HK is, as I had already told you, is a polynomial of the form okay. So now how to compute this easily?
So sir, here S0, S1 is the ASCII code.
Yes, like as we said, like you could take int of S0 as S0 and so on and so forth. Okay.
Okay, sir.
So let's say A is equal to 33. Okay, we saw that empirically A is equal to 33 is a good choice. Okay, so how do we compute this easily? So this can be done using the Horner's rule. Okay, so HK can be rewritten as okay. So why did we make this change? Any thoughts?
So it would be easier to do it iteratively,
It will be easier to have an
easier to
iterative
perform.
computation. Yeah, easier to have an iterative computation for this function. Okay, so let's say now we can easily compute the Okay. Any problems with this?
Sir, what is v dot length?
V dot length is the length of the string.
Sir, but
V
it
is,
is a number, right?
V is the strength, V is the length, V is the string, and V dot length is the length of the string. Yes, it's a number. It's strlenv.
Sir,
Uh,
sir, can you hear me?
hello?
Hello, sir, can you hear me?
Yes, I can.
Sir, while choosing that a equal to 33 apart among those empirical values, do we have to check any other factor, or we could randomly pick one of those empirical values?
You can take any one of them. I just chose 33 for an
Okay.
example.
So can't we say that as there are only 26 letters, all values greater than equal to 26 will be good enough?
I don't understand. What does that mean?
Uh, all the one digit, let's say for we take 26, so all the one letter words will be enumerated from 1 to 26, and when we get to the two digits, the first one is AA, which will get 27. So this way we are enumerating everything, so we will not have a collision, right?
Why? Because like your memory is limited.
Yes, sir, and yeah, the memory is limited, but I am just enumerating everything, and 26 is the smallest possible value. So the hashing value will be the smallest in this way.
I'm not getting you. Like, so
So
what are you
let's take
talking
the
of?
number
Are you
as a
talking
string with
which number?
n.
Which number?
So
Which
the
number are you
enumeration, the
talking?
hash of a word, I
Yes.
can say that
The hash of a word is an integer.
yes, sir. So I'll say that the word is written like in decimal we have like 10 digits, so the word is like an alphabet with 26 digits, and I just enumerate it like that.
Mhm.
So with a equal to 26 we are doing exactly that, so will it not give an
Which a,
unique value?
which a, like this a are you talking about, or what?
Yes, sir. A in this value, yes, this a which you
So
have
you have
taken
to
as
tell
that.
me that, like this a you are talking about.
Yes,
Okay.
sir.
So this is, as I say, this is an empirical observation. Okay. One can experiment with 26 and find out what is the number of collisions. So this is an experimental observation that was done.
So
So there
can
will
we
be
just show that theoretically 26 just avoids all?
no, because
So
there are
after
repeated.
modern, there will be collisions. Before
Yeah,
that, there
after
was.
modern, yeah, that's the
Okay.
problem. After modern, there will be collision. So see this. That's why I'm telling.
Okay, sir, understood.
So
So
what
that's
is
why
the
I said that like it is limited by your memory size, and that means that it is modulo n. Huh?
Okay, sir. Got it.
here? What is the choice of n?
What is the
Choice of n. Like
what is so that is a design choice. Like you can keep it like to some number that you like want your dictionary size to be. So this is an engineer's choice.
so, if we assume that these strings are the names, then the size will be at most, I mean, more likely 10. Then what will we choose?
No, why 10? So this is limited by your memory size. Suppose your dictionary, suppose somebody has given you a dictionary size of say 1000. Okay. So you will choose the closest prime to 1000. That's all.
Okay.
So as I say, this is a design choice. and this will be given to you. So that's why this is an input. This will be typically given to you. This is kind of a budget that is specified. However, none of you noticed one issue.
Sir, H can overflow.
H can become very large. Then what to do?
Take
So
modulo.
do modulo in every iteration.
So you do the modulo n, use the modulo property so that you can have the modulo n directly in the iterative computation.
Sir?
Let me finish, please.
Okay, sir.
Yeah, go ahead.
Sir, the values will change after this step.
Which values will change?
Means the hash value, sir, of each string. Like
Is
I'm
it?
not sure. Means no, sir, I'm not sure about it.
So your string, what is your name? Tell me.
Dhruv, sir.
Dhruv. Right? So Dhruv comes in. Okay.
Yes, sir.
And you have to find a hash function for Dhruv.
Yes, sir.
Okay. So the first entry here is
B of ID.
D. Okay. Int of D. Okay.
Yes, sir.
Modulo n. So that goes into H.
Yes, sir.
In the next step, what happens?
A into H plus H, int of H.
So that is two numbers, DH, they get hashed.
Yes, sir.
Two strings. Then DHR get hashed.
Yes, sir.
Then
DHRU gets hashed.
DHRU gets hashed. Then DHRU V gets hashed. At this point, your V length has exhausted.
Yes, sir.
So finally, you return H. So here it contains the hash of DHRUV.
Yes, sir. Sir, this value would be different from the above function, sir.
No. No. That's the beauty of modulo. Okay, you can check it. That's the beauty of modulo. So sum of modulo and modulo of sum are same.
Yes, sir. I heard it.
Sir, we need to convert vi into integer.
It's assumed that when you are writing it like this, it's an integer. So we are not writing like Toto C code. This is a pseudocode.
Okay, sir.
Okay, so now we have talked a little bit about the choice of hash functions. However, you remember that I told you that a good hashing strategy depends on two things. One was choice of hash functions. Okay. And the second one was, what was it?
Avoiding collisions.
Yeah, collision avoiding. Okay, since we already agreed that completely avoiding collision is out of scope, is impossible. So we need to have collision avoidance techniques. And what could be the different techniques? So basically, there are two major families of techniques. One is called chaining, okay, and the other is called open addressing. Here again, the most common one is linear probing. And then people also do techniques like double hashing. And then there are others also. But we will look into mainly these two, like for all practical purposes, looking into these two suffices. Okay, so the first among this is the chaining technique. So what do you do in the chaining technique? So as the name suggests, there is some idea of chains involved in this type of collision handling. Okay. So what do we do here? Each cell in the hash table is linked with a linked list, aka a chain. Okay. Now, if there is a collision, colliding items are stored in this list outside the table. Okay, let's look at an example and then we will try to like dissect it better. Let's say we again have keys equals to birthdays and elements as names. Okay, elements as names of persons. So now the hash function that we use here is month of birth modulo 5. Okay, let's say we have designed the hash function like this. Now in this case, let us say if our table structure looks like this, then and suppose our first entry is the following person. Okay, so then the birth month is 1 here, and therefore this will hash to this cell. As I said, the entries or the values are stored separately in a linked list that is connected to the main hash table. Now say the next entry is This goes here. Now say we have a colliding item. Okay, so we extend the list and include the colliding item here. Okay, so this is the idea of separate chaining. Yes.
Sir,
Hmm.
sir, are we trying to maintain the 2D matrix type thing?
Kind of. You are trying to maintain a type of 2D matrix, but something even more relatable. Can you tell me, you have come across a very similar data structure earlier? Can you recall it?
Adjacency list.
Adjacency list. Very good. So this is very similar to the idea of adjacency list. Okay. However, there is a big problem with this kind of a method, this
Sir,
kind of collision handling.
One.
Worst case is order of one.
It is
Yeah.
not.
So the worst case is that all entries become part of the same chain. Okay, so this is the worst case situation. So therefore, although this is a very simple technique, this is not usually recommended unless you have a nice idea of the types of keys that you are going to get and you know that the keys are pretty separable. Okay.
hello, sir.
Yes.
Sir, in the linked list, shouldn't we insert at the front?
No, there
Otherwise,
is
we have
no.
to traverse the linked list altogether at
So
each time.
yeah, so that is equivalent for any one of them, right? Suppose you are searching John, then if you put John at the end, so depends like, so you don't have any a priori idea about which among these will be you know, more uh, populous in your search items.
At least while construction, we can insert at the front so that we don't have to traverse the list again and again.
But that, again, remember, construction is a single time task.
Yes, yes.
It's the search that is important. So this is that you have to understand the differences between pre-processing and like continuous processing. Okay, so now we are coming to the close of the this course. Now these ideas should be more clear. These intuitive ideas should come more clear. So every time you get a problem, try to think about which part of this is continuous and which part of this is like pre-processing or one time. Okay, so one time you can invest more. Okay, that's why like you typically have like payrolls stored in such a way as so people don't really care about like how much time it takes to store. People only care about how much time it takes to retrieve the data. Okay, that is what is important because that is something that is going to happen continuously. Storing happens like once in a while, either like when a new employee joins or when a new employee leaves. Okay.
Sir, so the main reason we used hash table was the order of one searching. That is, we don't need to traverse, but in linked list we have to go through all the items. So,
not necessarily. Not necessarily. If your search item is John, you can have you search in order one. If your search item is like it is bounded by the number of collisions here. The traversal time is bounded by the number of collisions, unless it is the worst case.
no, sir, I'm saying that in the linked list, suppose if I'm traversing from first to right, And if it's the last item, so we're actually going through all the items, just like as an array.
Yes, but
That is we simply added the items without any
yes,
just
but
hashing and those.
yeah, yes, but like no, it is still hashing. Why? Because how many movements you need to do on the linked list? What is the
Sorry,
count?
that's
Huh?
here 4.
No, not
0,
4.
0 to
You
1,
just
1 to 2, 2 to 3, and 3 to 4.
no. You just map to this key value and then you directly move on the linked list.
Yes, the mapping, yes.
The mapping is still order
Sir,
1. Yes. No.
sir,
Well,
will
let's
there
do
be
one
any?
by one. Let's do one by one. The previous person, is your doubt clear?
Yes, sir, yes, sir. I got it.
Okay. Second person, yes.
Sir, will there be any use if we use hash table to store the colliding values?
Please wait. We will do exactly that in open addressing. So this is one idea that we just now talked about. Okay. So now we will talk about open addressing, where exactly what you said will be done. So what do you do here? The colliding items are placed in a different cell of the table. Now, the moment I say this, the question that arises is that which cell? Okay, if I say different cell, then which cell should I actually consider? And here comes different choices. The first and the very celebrated and most popular choice is what is called the linear probing technique. Is the linear probing technique. So what do you do here? Typically, colliding items are stored just at the next location. Okay, next location, but the notion is circular. Since it's a modulo operation, the notion is circular. So colliding items are just put in the next circularly available cell. Now then, testing if cells are free for inserting elements. This is what is called probing. So basically, you are probing the different cells to find out whether a particular cell is available for storing an element. Okay. So let us take an example. Let's say again, hx and let us say we have to insert the following numbers. Okay.
Sir,
Yes.
so this essentially means that we cannot have more than 13 numbers, right? Because then the pigeonhole principle comes and we cannot
Exactly.
avoid it.
Exactly. Yes.
Sir,
Hmm.
sir, in the previous method, would there be any collision?
Which previous method?
Sir, the maintaining the edges, chaining, sir, chaining.
There will be, yes, of course there is collision.
Sir, since we are storing all the colliding things in another, I mean,
No.
different location.
So the collision is handled in this way. This is an engineering choice by which you are handling the collisions. Collisions are there. You are handling the collision in this way. And therefore, like there might be a situation that all birthdays in your data set or all birth months in your data set actually modulo to 3. Okay. And therefore, you will have only one single chain of all the different elements.
Okay, sir, understood.
Collision is definitely there. This is a way to, so remember, this is a way to avoid collision. Collision handling means avoiding collision. This is one algorithm to avoid collision. The other one is what we are looking into now. So 41 will hash to
2.
2. Okay. Now next, 18 will hash to
5.
okay. 22 will hash to 9. What about 44?
So,
For 44?
5.
5.
Five,
So
sir.
now 44 comes here. There is a collision. So you probe for the next cell. Okay. You probe for the next cell. The next cell is free. So you insert 44 here.
But sir, if later on we get a key,
We will see how do we search. We have not talked about search. This is only about construction. Okay. We'll see what to do when we do searching. So 44 comes here. Now 59.
7.
Okay. 32.
6.
32, 6. So 6 is not available. 32 comes here. 6 is not available. 7 still not available. 8. So you keep on probing. 8 is available. So 32 goes and sits here. Okay. 31.
5.
5. 5 is again 31 comes here. 5 is not available. Go to 6. 7 is not available. 8 is not available. 9 is not available. 10 is available. So you put 31 at 10 and then 73 to 11 because again 73 hashes to
8.
8. Okay. So in this way you do the insertions. Okay. However, colliding items might lump together and therefore this might cause new collisions. So we need to do something. Okay. So colliding items will soon lump and this can cause more collisions. But before we talk about this more, we have an important task to do, the most important task, that is searching. This is the reason why we constructed such a data structure in the first place, and we want to do a searching. Okay, so suppose the find k function gives me the searched item. Okay, now how do I envisage to do this? So we will start from which cell should we start from?
Hash value.
The hash.
HK.
HK. Okay, and then we will keep probing until what are the conditions? An item with key k is found or what next?
Hash value is empty.
Hash value is
I
empty.
mean, table remains empty.
An empty cell is found because even after probing, you don't find the element and you landed up into an empty element, empty cell. That means that element was never inserted. Okay? Or all the n cells have been probed unsuccessfully. Okay.
Sir,
Yes.
sir, can you please scroll up a bit? The above
More?
example. The above example. Suppose in this one, if we have two more elements and both have keys 12. So what about the last one, last element? Where will it?
That will go to 0 circularly, as we said.
Oh, okay, right. Okay.
We can also write a pseudocode for this, following the same idea. This array is A. Array or table, whatever you call it. So this is the same pseudocode. This part is under the while loop. So this is the same pseudocode, like the same thing that we wrote in steps here is enumerated as a pseudocode. It might be a nice idea to like write some small code snippets around, like some hash tricks. Okay. Also, it might be a good idea to go and check like the hashing technique that the STL library uses. We will stop here. Yes. Any questions?
Yeah, means
So what?
how does this ensure that it is O1 search? It is still ON only.
ON.
Means
Why?
order we wanted constant time searching, right? But
Yes.
how have we achieved that using this construction? Still there may be order n time search.
In the worst case, it could be order n. But like so, if there is imagine your set of keys are such that there is no collision or very less number of collisions. You have designed a hash function in such a way that your collisions are very low. Then
Yes, sir. In that case, it will take place in constant.
that is what is the so basically here do not think about like this kind of iterative steps. I think this is what is bothering you. Think about like how your hash function is designed. So there is a lot of design principles that are going on here. It's no longer like a simple while loop. Okay, so you have to start thinking like designers. So you have say you have designed a very nice hash function which itself has some guarantees on collision. Okay, then you will never reach this worst case condition.
Sir, is it better than chaining?
Depends. So chaining
So I
has
think
this
chaining is better because
no
there
chaining
also
has
when
this
the
no chaining has this huge memory usage. See, everything in chaining might land up to one long linked list.
yes,
Additional memory, isn't
Sir,
it?
but chaining can handle more elements than n. This cannot handle that.
No, that's not. Yeah, that's true. That's true. That's true. That is so. There are advantages and disadvantages both ways.
And also,
so
sir,
only
in
in
this
terms
we
of
can
memory, I
have like
guess.
very high number of collisions in
Uh,
uh, in linear probing
Not really.
because
Depends on depends on how your hash function is designed. You might not use like a modulo n function as a simple. So see, you are getting guided by this particular example. Okay, imagine that you are writing a hash function which is very similar to the string polynomial that we wrote, but you are using a collision handling technique like linear probing. That is possible, right? This is an integer example that I have taken for giving a dry run on the technique. But like essentially in real world, you will not use this kind of simplistic examples. Agreed? Sounds reasonable?
yes, sir. And sir, how much of a problem is this lumping? Because how
This
many we have
is yeah.
used?
So basically what they do is I don't know whether you guys have heard about this word called garbage collection. So this is something very similar. So after some time, so it's like having puffed rice in a bottle. So after some time you need to shake it and like you need to again redistribute it. So there are ways, there are smart techniques to do it. We'll not cover that in the class, but like there are ways to handle this problems of lumping. You do some additional techniques to respread it. In fact, there are these ideas of double hashing also, which tries to some extent to reduce this lumping, which we will look in the next class.
Okay, sir.
Okay.
Sir, stop the recording, please.
Yes, I'm trying to stop, but seems like my pad has hang. Yeah.